Welcome back. We've introduced three different algorithms so far that can infect an executable with a virus you write. It'll be good to compare them since they come with different trade-offs. Before we do that, let's quickly go over how they work. The text padding infection takes advantage of the memory access control granularity. Between the executable segment and the next segment following it, there will be at most one page of padding that is unused, and that's where we inject the virus. The reverse text infection exploits the fact that the executable segment's start address for non-PIEs is usually fixed. The memory before this address is not used, and we reversely extend the segment to accommodate our virus. The PT node infection relies on a rarely used node segment and repurposes it into an executable segment that can be loaded and run our virus. This table sums up trade-offs between these algorithms pretty well. The PT node infection allows us to inject an arbitrary size of virus as long as our memory fits. The text padding provides the least amount of space, but one page is still enough for many small viruses. The reverse text infection unfortunately only works for non-PIEs, and it will likely have the lowest infection rate considering modern compilers by default link executables as PIE. Both PT node and reverse text infections are pretty easy to discover, even with just bare eyes. The reverse text infection has the highest complexity because we have to shift all sections to make space for our virus. This leads to more code to perform the infection. With our virus framework, it's trivial to set up experiments to compare algorithms. Let's try and infect all binaries under user bin with PT node algorithm first. It's able to infect most of them except ones that are compiled from Go. It's really hard to go wrong with this method most of the time. Now let's see the text padding algorithm. It works equally well because the test virus we're using here is extremely small. It failed for those that don't have enough gaps between the executable segment and the one right after it. This algorithm will likely have lower infection success rate if we want to drop a more complicated virus. Now let's try the reverse text infection. Unfortunately, most programs are compiled as PIE, which makes them immune to this infection. Only the Python interpreter and GCC toolchains are compiled as PIEs, and we're able to infect them. Everything is a trade-off, and there's no the best infection algorithm. It really depends on things you want to achieve. Some of you might ask, how do we come up with new infection algorithms? There are at least a couple things you need to think about. The first one is where to inject a virus to a file. Just like the text padding infection, maybe there exist other paddings in the ELF file structure that we haven't discovered yet. The readelf and obj dump tools will be your best friend to experiment and inspect file structures. Inspired by the PT node infection, perhaps there are other sections that are not needed for most programs to work. At runtime, we need to find a good place in memory for our virus. Can we create a new segment just for our virus without changing everything else? I'm sure we could come up with a brand new algorithm, but you also need to think about the complexity and effectiveness. We introduced three working algorithms already that need on average of 100 lines of code to infect 80% of the programs out there. But if something you design needs 10,000 lines of code to infect 30% of programs out there, it's probably not worth your time or effort. Although a good learning experience, the development and maintenance of such infection algorithm doesn't yield as much return. It's probably not something you should pursue. At this point, it's a better choice to focus on optimizing the virus code itself rather than the infection algorithm. When this video was recorded in 2024, the infector tool utilizing these algorithms was not flagged as malicious by any antivirus vendors, nor were any infected binaries. None of them recognized even the most obvious red flags, such as the presence of multiple executable segments. This concludes the chapter on virus infection techniques, and I hope you enjoyed studying these algorithms and understanding the things they exploit. You now have the skills needed to create your own unique infection method. In the next chapter, we'll discuss how to perform redirection, the final step to making a virus run as a part of an infected binary.